So there are two different types of factoring we're going to learn today, and these are both special cases of factoring. So the first is difference of squares, and the second is perfect square trinomials. So before we learn how to factor difference of squares, we're going to remind ourselves of how we multiply conjugates. So remember, a conjugate is when you have two binomials that are the same but have opposite signs. So we distribute our m times m gives us m squared, m times 5 gives us 5m, and then distribute our negative 5. Negative 5 times m is negative 5m, and negative 5 times 5 is negative 25. So what ends up happening is these two terms in the middle are the same, but opposites, so they cancel each other out. When we simplify, we get m squared, which is a perfect square, and 25, which is a perfect square, and we are subtracting those. So that's where we're getting this difference of squares is from subtraction. So when we see a binomial that is a difference of squares, binomial, remember, two terms, we can factor it to conjugates. So let's take a look at a few examples. Our first one, we've got n squared, which is a perfect square, and so is 121. And they are all difference of squares because they are all subtraction. If you are adding perfect squares, you cannot factor those. So first thing we do is find the square root of the first term. The square root of n squared is n, and the square root of 121 is 11. So these are the two pieces that will go in my conjugates. We'll have n plus 11 and n minus 11 in either order. So just to check our work and make sure we understand where this is coming from, n times n gives us n squared. And remember, when we multiply conjugates, there was that shortcut where we could do the first two terms times each other, and then the second two terms times each other, minus 121. So that gets us what we started with. Looking at the second one, the square root of 49 is 7, and the square root of k squared is k. The square root of 144 is 12, so those are the two pieces for our conjugates. So we get 7k plus 12 and 7k minus 12. And again, you can put that plus and minus in either order. Last example, we're going to find the square root of 81, which is 9. The square root of a squared is a. The square root of 64 is 8, and the square root of b squared is b. So when we factor this, we get 9a minus 8b and 9a plus 8b. So go ahead and pause here to try these two examples. All right, so the answer for these would be 3n minus 7 and 3n plus 7 in either order. And for our second one, we would have 2a minus 5c times 2a plus 5c. Next, we're going to take a look at factoring difference of squares with a GCF. So the first thing we need to do is find the GCF to factor it out. So for 3 and 27, my GCF is 3. Dividing that out of each term, I have x squared, and 27 divided by 3 is 9. And then you look at what's left to see if you can continue factoring. X squared and 9 are both perfect squares, so the square root of x squared is x, the square root of 9 is 3. So when I factor that into my conjugates, I'll have x plus 3 and x minus 3. And don't lose your GCF that you factored out in the first place. My second example, I do not have a difference, I have a sum. So what I'm going to do on this one is factor out a negative, since my first term has a negative. So I notice 5 is my GCF, I'm going to factor that negative out with it. And I also notice that both terms have a y, so I'm going to factor a y out as well. So negative 20 divided by negative 5 is 4. Y cubed, when you factor one y out, you have y squared left. Positive 45 divided by negative 5 is negative 9, and we factored out the y. So now we find the square root of each term. The square root of 4 is 2, and the square root of y squared is y. And the square root of 9 is 3. So we keep our original GCF, our negative 5y, and then the 2y and 3 are the pieces for our conjugates. so 2y plus 3 and 2y minus 3. Last example, I'm noticing a GCF of 2, and since my variables are different, I can't factor any variables out. So 2 divided by 2 leaves me with the a squared. 200 divided by 2 is 100, leaving me with the b squared. And then I find my square roots. Square root of a squared is a, square root of 100 is 10, square root of b squared is b. So I keep my GCF of 2, and then I use my pieces for the conjugate a minus 10b and a plus 10b. All right, 2 more try problems. First example, we have a GCF of 6, leaving us with 1 minus 4w squared. So we factor that to 6 times 1 minus 2w, 1 plus 2w. Second example, we have a common factor of negative 2, leaving me with 16d squared minus 25, which gives me negative 2 times 4d plus 5, 4d minus 5. All right, our last special case is the perfect square trinomials. So what we're going to do with this is end up factoring them back to a binomial squared. So I want to remind you of how we square a binomial. We do not distribute the 2. To square something means to multiply it by itself. So I'm going to take w plus 7 times itself. Distributing, I get w squared plus 7w plus 7w plus 49. So I'm going to write this a little differently than we saw before when we combined our like terms. Notice that my first term, w squared, is a perfect square. My middle 2 terms are the same thing, so I can rewrite that as 2 times 7w. And then my last term is a perfect square as well, and in fact, the square root of 49 is 7. And the square root of w squared is w. So those 2 square roots are doubled to give you the middle term. So I'll show you how this works when we're factoring. So the first thing we need to do is make sure that the last term is positive, because anytime you square a number, whether it's positive or negative, you get a positive answer. So your constant always has to be a plus for it to be a perfect square trinomial. And your first and your last terms both need to be perfect squares. So the square root of x squared is x, and the square root of 64 is 8. So we use those to check our middle term to see if the pattern holds. We always need a 2, because we have 2 of the same thing when we factor it out, when we multiply it out, multiplied by the square root of our first term and the square root of our last term. So 2 times x times 8 does give us 16x. And then this sign right here will be the sign in our binomial. So when we factor this, we get the x minus 8 squared. And for those that are a little lost, let's check our answer and see how this works. Remember, when we square a binomial, we multiply it by itself. So I'm going to distribute my x to get x squared minus 8x. Distribute my negative 8 to get negative 8x plus 64. So notice how I have 2 times the 8x in the middle, and then that sign on the negative 16 is what gave me my negative. So when I finish simplifying this, I get x squared minus 16x plus 64. Next one, the first and the last terms are perfect squares, so I find the square root of those. Square root of 25 is 5. Square root of y squared is y. Square root of 1 is 1. And then I double check my middle term. 2 times 5y times 1. We need 2 of those terms in the middle, because when we multiply out, we get 2 of the same terms. So 2 times 5y does give me 10y. So when I factor this, I get 5y plus 1 squared. Last example. Again, my first and my last terms are perfect squares. So I find the square root of each term, 2v, square root of 49 is 7. So I check my middle term, 2 times 2v times 7. 2 times 2v is 4v times 7 is 28v. So when I factor this, I get 2v minus 7 squared. All right, and a couple of try problems for you. So to factor our first one, the square root of the first term is 3g. The square root of the last term is 10. Double check your middle term. 2 times 3g is 6g, times 10 is 60g. So we get 3g plus 10 quantity squared. In the second example, square root of this is 9k, square root of 16 is 4. So we double check our middle term, 2 times 9k times 4. This time I would multiply my 2 times 4 first to get 8. 8 times 9k is 72. So when I factor this, I get 9k minus 4 squared.